For most of human history, Mars looked simple, a cold red point moving slowly across the night sky, dry, empty, silent. Even after spacecraft finally reached it, the picture barely changed. Orbiters mapped endless deserts, landers touched down on barren plains. Rover after rover found evidence that water once existed there long ago, but the larger conclusion stayed mostly intact. Mars had died billions of years ago. Then, in 2021, a small rover built by China landed on a flat plain called Utopia Planitia. It traveled only 1.2 miles before falling permanently silent less than a year later. But in that short distance, it found evidence that forced scientists to reconsider some of the most settled assumptions about the history of Mars. The rover detected signs of water activity from as recently as 400,000 years ago, a geological moment compared to the timelines researchers previously accepted. It identified unusual structures buried roughly 35 meters beneath the surface using ground penetrating radar, shapes and layers that do not fit neatly into existing models of a dead desert world. And it may have landed directly beside the shoreline of an ocean that once covered nearly a third of the planet. The rover itself was named Zhurong, after a Chinese god of fire, and despite operating alone on another planet, powered only by sunlight and delayed radio commands from Earth, it became only the second rover in human history successfully operated on Mars by any country. What makes the mission stranger is that the discoveries did not stop when the rover did. Years after contact was lost, scientists are still publishing new analyses from the data it collected before going quiet. A dead rover on a dead planet is still changing planetary science. If this kind of content helps you unwind at night, consider subscribing. We put out new space documentaries regularly, and having you here means a lot. It starts with the version of Mars scientists thought they already understood. Long before any rover crossed the plains of Mars, we had already built a story about the planet in our minds. It was a story assembled slowly across generations of telescopes, probes, failed missions, and patient measurements. By the early 21st century, that story felt almost complete. Mars formed around 4.6 billion years ago from the same collapsing cloud of gas and dust that created Earth. In its earliest era, the resemblance between the two worlds may have been startling. Ancient river valleys cut across the surface. Delta formations spread outward where water once emptied into standing lakes. Mineral deposits revealed long contact with liquid water. Some climate models even suggested a northern ocean covering millions of square kilometers. For a time, Mars was active, warm enough for rain, thick enough in atmosphere to hold stable water at the surface. Volcanoes reshaped the terrain while groundwater circulated beneath the crust. If you could have stood there billions of years ago, you may have recognized parts of it, but the planet was smaller than Earth. That difference mattered. Smaller planets lose internal heat faster. As Mars cooled, its core gradually solidified. The magnetic field collapsed with it. Without that invisible shield, the solar wind, a continuous stream of charged particles flowing outward from the sun, began striking the atmosphere directly. Over immense stretches of time, the atmosphere thinned away molecule by molecule. The process was slow, relentless. By the Amazonian epoch, beginning roughly 3 billion years ago, most planetary scientists believed the transformation was complete. Mars had become hydrologically dead, meaning stable liquid water no longer shaped the planet in significant ways. Geological activity appeared minimal, surface change slowed dramatically. What remained was a frozen desert, preserving the memory of a wetter past. This conclusion did not emerge from speculation. It came from decades of accumulating evidence. Orbiters mapped dry valleys and cratered plains in extraordinary detail. The Viking missions in 1976 sampled the soil directly. Later rovers, Spirit, Opportunity, and Curiosity, confirmed ancient water chemistry again and again while also reinforcing the larger timeline. Water had existed, then it vanished. Utopia Planitia fit perfectly into that framework. The immense northern plain had been photographed from orbit for decades. It appeared monotonous almost beyond description. Flat terrain stretched toward the horizon with little visible structure or variation. Viking 2 landed there and found exactly what scientists expected: dust, rock, cold air, and silence. Nothing about the region suggested urgency or mystery, so when engineers and researchers prepared the Zhurong mission, they were not expecting revelation. The goal was refinement, better measurements, higher resolution data, more precise confirmation of an already established planetary history. It did not confirm what was already known. At the edge of the South China Sea, rockets rise through air so humid it softens the horizon. On July 23rd, 2020, one of them carried a mission called Tianwen-1 into the morning sky from Wenchang Space Launch Center on Hainan Island. The name came from a poem written more than 2,300 years earlier. Tianwen means questions to heaven. The poem asks why the cosmos behaves the way it does, why the stars move as they do, why worlds exist at all. It was an ancient title for a very modern act. Inside the spacecraft were three separate machines: an orbiter, a lander, a rover, all launched together. No nation had attempted that combination on its first independent Mars mission. Mars exploration has historically been brutal to newcomers. The Soviet Union launched 19 Mars missions before achieving even a partial operational success. The United States lost multiple spacecraft before Mariner 4 finally returned flyby images in 1965. Failure has always been part of the planet's reputation, but Tianwen-1 worked. 7 months after launch, the spacecraft entered Martian orbit. Then came the harder part. Landing on Mars means surviving atmospheric entry at hypersonic speed, deploying parachutes in an atmosphere barely thick enough to slow you down, igniting rockets at exactly the correct altitude, and touching the surface gently enough to avoid destruction. Chinese engineers called the sequence the 9 minutes of terror. You can hear the echo of earlier Mars missions in the phrase. Different countries, same problem. On May 15th, 2021, the lander reached Utopia Planitia safely. Days later, a ramp unfolded onto the dust, and the rover rolled forward for the first time. Zhurong weighed roughly 240 kilograms, close to the mass of a large motorcycle. 6 wheels carried it across the plain. Solar panels unfolded like wings. Mounted across its body were 6 scientific instruments designed to study the atmosphere, magnetic environment, surface chemistry, and hidden structure beneath the ground. One instrument mattered especially. The rover carried ground-penetrating radar, usually shortened to GPR, a system that sends electromagnetic pulses downward into the soil and measures the returning reflections. Different underground materials reflect signals differently. Ice responds one way, rock another, layered sediment differently again. Zhurong's deep radar could probe nearly 100 meters beneath the surface while driving continuously across the terrain. No previous rover on Mars had carried surface radar with that depth capability. The landing site had been chosen carefully. Orbital observations hinted that ancient water ice might survive below the plains of southern Utopia Planitia beneath thick layers of sediment and dust. The expectation was cautious confirmation, buried ice, frozen history. Another data point inside an already familiar planetary story. But the signals returning through the Martian ground did not resemble a simple frozen reservoir. They resembled something far more complicated, and now the rover was moving, slowly, quietly, with about 1 Martian year before winter sunlight began fading across the plain. If you stood beside Zhurong during its first weeks on Mars, the landscape would not have looked extraordinary. The horizon stretched outward in muted browns and pale reds. The terrain rolled gently beneath scattered rocks and shallow ripples of dust. Nothing about the view suggested catastrophe, but the rover was sitting inside one. Utopia Basin is the largest confirmed impact structure in the entire solar system, a depression roughly 3,300 kilometers across. To picture that scale on Earth, you would need to imagine a crater wider than the continental United States from the Atlantic coast to the Pacific. It is so large that ordinary human intuition stops working around it. The basin formed approximately 3.9 billion years ago during the late heavy bombardment, a violent era when the young inner solar system was still crowded with leftover debris from planetary formation. Asteroids and protoplanets crossed unstable orbits continuously. Worlds were struck again and again. Something enormous hit Mars. The impact released energy beyond comparison with any event in human history. The crust collapsed downward by several kilometers across a region larger than Europe. Rock liquefied under pressure. Shock waves traveled through the planet's interior. For a moment, Mars itself changed shape, but time erased the drama from ground level. Inside the basin, the curvature of the depression is so gradual that its boundaries disappear below the horizon. Zhurong drove across terrain that felt almost perfectly flat. The rover could never see the walls surrounding it because those walls were unimaginably distant. You could spend an entire lifetime crossing the basin floor without understanding the structure beneath your feet. From orbit, though, the geometry becomes unmistakable. The northern hemisphere dips inward in a vast circular arc visible from space, a planetary scar preserved across billions of years. Scientists studying topographic maps noticed something else about that depression as well. It occupied one of the lowest elevations anywhere on Mars. That detail mattered. For decades, planetary researchers proposed that Mars once possessed a northern ocean covering much of the lowland hemisphere. If such an ocean existed, Utopia Basin would have formed a natural collection point for the water, a giant bowl capable of holding a sea stretching across millions of square kilometers. Attention gradually focused on the basin's southern boundary, where the flat floor rises into a curved escarpment, a steep transition between lowland and highland terrain. Some researchers believed this escarpment represented an ancient coastline left behind as water levels changed over immense spans of time. Zhurong landed almost directly beside it, not by accident, by design. No previous rover had been positioned with such precision at the suspected boundary between ancient shoreline and ancient seabed. Orbital images hinted at patterns worth examining more closely, but orbiters always look downward from hundreds of kilometers above the surface. They cannot stand at the edge of a slope and study the rocks directly. Now, for the first time, cameras on another world were looking outward from the ground itself toward the possible edge of an ancient Martian ocean. The escarpment did not tower like a mountain. It rose gradually from the plain, a long sloping ridge curving across the landscape with a shape subtle enough that, from orbit, scientists debated for years what they were actually seeing. Now the uncertainty narrowed. As Zhurong drove southward, its cameras captured the first close surface images ever taken of the formation. Rocks emerged from beneath thin sediment layers, outcrops broke the smooth terrain. The slope itself revealed textures impossible to distinguish from orbital altitude, including fractured ledges and exposed faces carved into irregular horizontal patterns. The rover's spectrometer began analyzing the minerals scattered along the base of the escarpment. A spectrometer identifies substances by measuring how they absorb and reflect light across different wavelengths. Certain minerals leave unmistakable optical fingerprints. One signal stood out immediately: hydrated silica. On Earth, hydrated silica forms in environments where liquid water remains present over extended periods of time. It appears around hydrothermal springs, lake margins, seafloors, and mineral rich coastlines where water continuously interacts with volcanic rock and sediment. Finding it concentrated along the base of the ridge mattered because the mineral itself records long contact with water, not brief isolated melting events. The geometry of the escarpment deepened the puzzle. Sections of the lower slope appeared undercut near their bases, with upper material extending outward slightly above recessed lower layers. On Earth, coastlines shaped by wave erosion often develop this same profile after water gradually removes weaker material near sea level. It is a slow process, repetitive, rhythmic. Mars no longer has waves, but the rocks still preserve shape. Near the base of the formation, Zhurong also imaged narrow sediment channels angling inward toward the basin floor rather than outward toward the highlands. Their orientation suggested material draining back toward lower elevations as water retreated, not rainfall flowing downhill from above. The direction of movement mattered as much as the channels themselves. Taken separately, each clue remained open to interpretation. Together, they formed a coherent geological story. The mission team published their analysis carefully, almost cautiously. Scientific language tends toward restraint even when implications become enormous. The paper described the findings as the first ground level discussion of a probable evolutionary scenario for a Martian ocean. Probable, not proven, but the scenario itself was striking. Over hundreds of millions of years, water may have pooled inside Utopia Basin until a vast northern sea covered nearly one-third of Mars. The escarpment beside Zhurong marked the ancient boundary where that ocean stabilized for long periods, leaving behind a mineral and erosional signature similar to a bathtub ring around the edge of a basin. As the atmosphere thinned and temperatures dropped, the shoreline retreated gradually across the landscape. At maximum extent, the ocean would have transformed the planet completely. On Earth, a sea occupying equivalent elevation would drown nearly everything below 2,000 meters, submerging most of North America beneath water reaching toward the Rocky Mountains. The shoreline was extraordinary, but the shoreline was not the most unexpected thing Zhurong found. The discovery began with dunes so small you could easily overlook them from orbit. Four low ridges sat scattered across the plain near Zhurong's landing area, each only about 15 to 30 meters long and roughly 1 meter high. From space they appeared unremarkable, shaped by wind like countless other Martian dunes already catalogued across the planet. But close inspection changed everything. As the rover approached, its cameras resolved delicate crusts covering portions of the dune surfaces. The crusts were thin and brittle, broken into geometric fracture patterns, spreading outward like dried mud on a desert floor after rain. The shapes were precise enough that planetary scientists recognized the texture immediately. Wind could not produce this. On Earth, similar polygonal cracking forms when mineral-rich water evaporates from sediment, leaving behind hardened salt deposits that later contract and fracture as conditions change. The geometry matched evaporative crusts found in arid saline environments where water briefly appears, disappears, and leaves chemical evidence behind. The implications became uncomfortable very quickly. Researchers examined the mineral chemistry of the dunes and identified salts mixed into the sediment. Salts matter because they dramatically lower water's freezing point. A salty liquid can remain fluid far below 0 degrees Celsius, under conditions where pure water would freeze solid. Mars regularly reaches those temperatures during warmer seasonal periods near the equator and mid-latitudes. The team proposed a specific sequence. Frost or light snowfall settled onto the dunes during colder intervals. When temperatures rose later, some of that frozen material partially melted after contacting salt-rich surfaces. Thin films of briny water formed briefly between sand grains, then evaporated or refroze as temperatures dropped again. The remaining minerals hardened into crusts that eventually cracked into the patterns Zhurong photographed. It was a subtle process, fragile, temporary, but it was still liquid water. The age estimate deepened the shock. Scientists dated the dune surfaces themselves and concluded the crusts likely formed between 1.4 million and 400,000 years ago. That range is astonishingly recent on geological timescales. 400,000 years ago, anatomically modern humans had already existed on Earth for well over 100,000 years. Mars was not supposed to behave this way. For decades, prevailing models placed the end of stable liquid water activity roughly 3 billion years in the past. Yet these dunes suggested that under the right seasonal and chemical conditions, water still intermittently reached the surface in liquid form extraordinarily recently. Geophysicist Xiaoguang Qin of the Chinese Academy of Sciences described the formations carefully, attributing them to liquid saline water produced through melting frost and snow on salt-containing surfaces. The phrasing remained conservative. The evidence itself did not feel conservative at all. This was not an ocean returning to Mars, not rivers cutting valleys again, nothing dramatic. Just a microscopic film of cold brine appearing briefly across grains of sand beneath a thin atmosphere and weak sunlight. But on Earth, life survives in environments exactly this marginal. Salt flats, polar deserts, frozen soils that thaw only for moments each year. If liquid water was still touching the Martian surface 400,000 years ago, the question beneath the ground became harder to ignore. Beneath the rover's wheels, invisible to every camera and untouched by every drill before it, the ground was storing a layered record of time. Zhurong carried an instrument built specifically to read that hidden archive while moving continuously across the plain. The system operated quietly, constantly. Ground-penetrating radar, usually shortened to GPR, works by transmitting electromagnetic pulses downward into the subsurface and measuring the returning echoes. Different materials reflect those signals differently. Ice produces one pattern, loose sediment another, dense rock another still. By tracking how the reflections change with depth, scientists can reconstruct buried structures without physically excavating them. Zhurong carried two separate radar systems operating at different frequencies. One focused on shallow detail, resolving structures within roughly 10 meters of the surface at very high resolution. The second penetrated far deeper, reaching nearly 100 meters into the Martian crust while sacrificing some fine detail for depth. Together, they created something unusually powerful, a moving vertical profile beneath the rover's entire route. The shallow radar immediately revealed complexity. Instead of uniform sediment, the upper layers alternated repeatedly between coarse and fine material. Some layers appeared dense and compacted. Others looked looser and more fragmented. The boundaries between them formed long, continuous horizons extending across significant distances. Scientists recognized the pattern as environmental cycling. Coarse layers often accumulate during energetic conditions, flowing water, flooding, rapid sediment transport, or active freeze thaw disruption. Fine layers settle more slowly through calmer processes such as dust deposition or quieter water environments. Wind can reshape both afterward, burying older surfaces beneath new material over immense spans of time. Each boundary marked change, a wetter interval ending, a colder interval beginning, sediment arriving from elsewhere, ice forming, retreating, then returning again. The subsurface beneath Utopia Planitia was not a single static deposit. It resembled a stack of preserved climates, layered one atop another. But the deeper radar transformed the mission entirely. No previous rover on Mars had produced a continuous high resolution cross section extending down 100 meters beneath an active surface traverse. Orbital radar systems already existed, including NASA's SHARAD instrument aboard the Mars Reconnaissance Orbiter. SHARAD scans the planet from roughly 300 kilometers above the surface and detects broad underground structures effectively. But altitude limits resolution. From orbit, you can identify large buried ice sheets or major geological boundaries. Fine layering becomes difficult to separate clearly. Zhurong operated directly against the ground itself. The difference resembled comparing a satellite photograph to a close geological excavation. Months passed while researchers processed the incoming radar returns. The dataset was enormous. Reflection patterns had to be modeled carefully against known Martian soil properties, temperature conditions, and signal behavior inside layered sediment. What emerged contradicted expectations. A geologically dead world should produce relatively uniform subsurface accumulation after billions of quiet years. Instead, the radar revealed variation everywhere, distinct depositional sequences, disrupted layers, reworked material, multiple environmental regimes superimposed across time. The ground beneath Zhurong looked active in its history, not dormant, and buried within those layers, at approximately 35 meters below the surface, sat a structure nobody expected to find in Utopia Planitia. The patterns first appeared as interruptions in the radar layers, angled structures cutting downward through the surrounding sediment in repeating geometric forms. They emerged consistently at roughly 35 meters depth beneath nearly the entire distance Zhurong traveled across Utopia Planitia. Researchers stared at the profiles carefully because the shapes looked familiar. Not Martian familiar, Earth familiar. The structures existed only in the radar data. No camera could photograph them. No orbiter could resolve them from above. Buried beneath tens of meters of accumulated sediment, they had remained invisible for billions of years until electromagnetic pulses from a rover crossing the surface revealed their outlines indirectly. On Earth, formations like these are called periglacial polygons. The process that creates them is well understood. Water trapped within soil freezes during cold periods and expands as it turns to ice. That expansion fractures the surrounding ground into polygonal crack systems. When temperatures rise again, the cracks partially thaw and fill with sediment, ice, or mineral-rich material. Repeated freeze-thaw cycling gradually deepens and widens the structures into wedge-shaped formations extending downward beneath the surface. The pattern repeats over enormous spans of time. In Siberia, Alaska, and northern Canada, periglacial polygons stretch across entire landscapes. Satellites photograph them by the thousands. They are among the clearest geological signatures that a region experiences long-term seasonal freezing and thawing involving subsurface water. That interpretation carried profound implications for Mars. If the buried wedges beneath Utopia Planitia truly represented periglacial polygons, then the region had once undergone repeated cycles of freezing and thawing deep underground. Not once, repeatedly. Water had persisted within the subsurface long enough to freeze, expand, melt, collapse, and reform over extended periods. The depth mattered as much as the structures themselves. 35 meters of sediment now sit above the polygons. That overlying material accumulated gradually after the wedges formed, likely through wind-driven deposition during increasingly dry climatic conditions. The polygons, therefore, belong to an earlier environmental era, preserved beneath younger layers, like fossils sealed inside rock. Researchers dated the formations to the transition between the late Hesperian and early Amazonian periods, approximately 3 to 3.5 billion years ago. That timing is important because planetary models traditionally treated this interval as the final stage of Mars becoming permanently cold and dry. But the polygons resisted that simple narrative. A single abrupt drying event would not produce repeated freeze-thaw structures extending across large buried regions. The evidence instead suggested a drawn-out transition lasting potentially hundreds of millions of years. Water remained present underground. Climate conditions oscillated. The environment shifted back and forth repeatedly, rather than collapsing all at once into permanent sterility. Freeze, thaw, refreeze, thaw again. The study announcing the discovery appeared in Nature Astronomy in November 2023, 18 months after Zhurong itself had already fallen silent on the Martian surface. The rover no longer transmitted. The science continued arriving anyway. And the polygons were only part of what the radar revealed. Every buried layer beneath Utopia Planitia carried its own fragment of the planet's memory, waiting for researchers to understand what the signals were saying. Imagine lowering a transparent slice through the ground beneath Utopia Planitia and reading downward through time itself. That is effectively what Zhurong's radar accomplished. Every buried layer represented a different environmental chapter preserved beneath the plane, stacked quietly beneath one another across billions of years. Closest to the surface, the structure looked familiar. The uppermost layers were thin, uniform, and remarkably fine-grained. These deposits matched what scientists expected from a cold and inactive Mars, dust carried by wind and settling gradually over immense spans of time. Little disturbed them, little reshaped them. The signals reflected a world that had become quiet. But deeper down, the textures changed. The radar began revealing thicker and coarser deposits, arranged in repeating bands beneath the surface. Coarse sediment behaves differently from fine dust. It usually requires stronger transport processes, flowing water, moving ice, energetic flooding, or sustained current activity capable of carrying heavier particles before depositing them elsewhere. The arrangement mattered as much as the material itself. A coarse layer appeared, then finer sediment above it. Beneath that, another coarse interval emerged, then fine again. The alternation repeated throughout the subsurface profile in a rhythm too organized to dismiss as random accumulation. Scientists studying the radar reflections identified at least 3 to 4 major depositional cycles extending through the layered column. That phrase sounds technical. Its implication was profound. Utopia Planitia had not experienced a single wet era followed by permanent planetary death. Instead, water activity appeared to return repeatedly across different periods of Martian history. Wet intervals emerged, faded, then emerged again under changing environmental conditions. Each cycle left behind its own buried signature before newer sediment sealed it beneath another layer. Mars pulsed. The deepest readable sections likely dated back to the Noachian period, the earliest major era of Martian history, when rivers, lakes, and perhaps oceans covered large regions of the planet. Those ancient layers aligned with long established models describing a warmer and wetter early Mars. The shallower layers created the real tension. Evidence of water-related deposition extended well upward into strata associated with the Amazonian period, the very interval scientists had traditionally described as hydrologically dead. Hydrologically dead simply means a world where liquid water no longer shapes the surface or subsurface in meaningful ways. But the radar data suggested otherwise. When researchers compared these buried depositional cycles with the dune crust evidence identified earlier, the pattern became harder to dismiss. Two independent datasets pointed toward the same conclusion. One came from surface mineral chemistry and recent saline activity. The other came from buried geological structure extending through deep time. Together they implied that Mars retained liquid water environments in some form billions of years longer than accepted planetary models had predicted. The findings appeared in National Science Review with carefully measured language stating that sustained aqueous activity, meaning persistent water-related processes, still existed during an era previously considered geologically dry. Scientists tend to write cautiously, especially when evidence begins challenging decades of consensus understanding. Claims become restrained. Conclusions narrow themselves deliberately. But beneath the restraint sat an implication everyone studying the data understood perfectly well, even if they avoided stating it too directly. At this point in the story, a certain thought naturally begins forming in the background. The evidence has been building layer by layer, water activity lasting longer than expected, buried freeze-thaw systems, chemically active sediments, minerals shaped through long contact with liquid environments. So, it is important to say something plainly. Zhurong did not find life. It detected no organisms, no fossilized microbes, no confirmed biosignatures, meaning chemical or structural traces directly produced by biology. Nothing in the rover's dataset proves that living things ever existed on Mars. But the mission changed the life question anyway. On Earth, life occupies environments once assumed impossible. Microbes survive inside hypersaline lakes in Chile's Atacama Desert where salt concentrations become extreme. Bacteria remain viable within frozen permafrost for millions of years. Entire ecosystems exist kilometers underground, sustained not by sunlight, but by chemical reactions between water and rock. These organisms are called extremophiles, life forms adapted to conditions once considered too hostile for biology: cold, dark, salty, buried. The environments described by Zhurong sound strikingly familiar: a subsurface region containing mineral-rich sediments, intermittent liquid brines, ancient groundwater activity, and long-term freeze-thaw cycling would not be considered sterile on Earth. In several terrestrial environments, those exact conditions support microbial communities remarkably well. The timeline matters enormously. If liquid water activity on Mars extended as recently as 400,000 years ago, then the potential habitability window for the planet expands dramatically. Astrobiologists use the term habitability window to describe the span of time during which environmental conditions could support life. Before these findings, many models treated Mars as biologically unfavorable for roughly 3 billion years. Zhurong shortened that dead interval substantially, not by proving continuous oceans survived into recent history, but by demonstrating that localized liquid environments persisted intermittently under the right chemical and thermal conditions. For microbes already adapted to Martian subsurface conditions, that distinction could matter profoundly. Then there is the silica. Along the ancient escarpment, Zhurong identified hydrated silica deposits associated with long standing water activity. On Earth, silica rich hydrothermal environments preserve biological material exceptionally well. Mineral rich water gradually entombs microorganisms, locking cellular structures into stone long after the organisms themselves decay away. Some of the oldest microbial fossils ever discovered on Earth survived because silica preserved them. If ancient Martian hydrothermal systems once existed near the shoreline of a northern ocean, hydrated silica is exactly the material researchers would hope to examine, and the location matters too. Ocean margins, shallow coastal regions, and mineral rich hydrothermal boundaries are among the most biologically productive environments on Earth. Astrobiologists would choose sites like these deliberately. That may be the most important shift Zhurong created. The rover did not solve the question of Martian life. It narrowed the search with unprecedented precision, identifying specific environments, specific depths, specific mineral systems, and specific geological periods where the probability of preserving evidence appears highest. The map became sharper. But before the mission could push further into that search, the rover itself stopped moving. Winter on Mars arrives slowly. Sunlight weakens week by week across the northern plains, shadows lengthen across the dust, and temperatures fall toward extremes that even hardened machines struggle to endure for long. By May 18th, 2022, Zhurong had reached that threshold. The rover depended entirely on solar energy. Its panels gathered sunlight during the day, charged onboard batteries, and powered every movement, transmission, and scientific instrument. But as winter approached Utopia Planitia, the available sunlight dropped sharply. The mission team had anticipated this from the beginning. The plan was controlled hibernation. Non-essential systems would power down to conserve energy, while heaters protected critical internal components from freezing. The rover would sleep through the coldest period, then reactivate automatically once spring sunlight returned strongly enough to recharge its batteries. The final data packet arrived. Then nothing. At first, nobody considered the silence unusual. The China National Space Administration expected the rover to remain inactive for months while winter passed overhead. Reactivation was anticipated around December 2022 when seasonal conditions improved across the landing region. December arrived. No signal. January followed. Still nothing. As engineers examined the situation, the most likely explanation emerged gradually. Dust. Mars is covered in ultrafine dust particles small enough to remain suspended in the atmosphere for long periods. Over time, they settle onto exposed surfaces, especially stationary equipment. During hibernation, Zhurong could no longer reposition itself or actively manage panel orientation. Dust accumulated across the solar arrays layer by layer until incoming sunlight could no longer generate enough electrical power to restart the system. The batteries never crossed the activation threshold. This outcome was sadly familiar in Mars exploration. NASA's InSight lander suffered nearly the same fate in December 2022. After 4 years of operation, its own solar panels slowly buried beneath dust accumulation until power levels collapsed permanently. But Zhurong's silence felt different, partly because the rover remained mobile until the end, partly because its landing site had become scientifically extraordinary. The mission had not exhausted the terrain around it. More radar transects remained possible, more geological boundaries waited nearby. the rover still had unexplored ground ahead when the transmission stopped. As of now, no confirmed communication has returned from the rover. Somewhere on the floor of Utopia Basin, a machine weighing roughly 240 kilograms remains motionless beneath the thin Martian sky. Dust covers the solar panels. The wheels no longer turn. The instruments sit dark and inactive inside the cold. But the mission itself did not end cleanly with the silence. The discoveries kept arriving afterward. Research papers continued appearing through 2023, then 2024. New analyses emerged from datasets already transmitted back to Earth and stored inside research servers in Beijing. Scientists kept finding patterns hidden inside radar profiles, mineral signatures, and environmental measurements gathered before contact was lost. A rover that stopped moving in 2022 was still reshaping planetary science years later, and that changes how we think about what a Mars mission actually is. In laboratories and research offices across China, the rover continued moving long after its wheels stopped. Not physically, computationally. Every radar sweep, mineral scan, atmospheric reading, and magnetic measurement remained stored inside enormous datasets, waiting to be processed in full detail. Planetary missions rarely end when transmissions stop. The public often imagines discovery happening in real time. A rover scans the ground. Scientists immediately understand the result. Then a conclusion appears days later. Real planetary science unfolds much more slowly. Data arrives raw, incomplete, and difficult to interpret. Signals overlap, noise contaminates, measurements. Geological models must be tested against competing explanations repeatedly before researchers trust what they are seeing. Zhurong's radar alone generated extraordinary amounts of information. Every meter of the traverse produced layered reflection profiles extending downward through the subsurface. Those reflections then required complex computational modeling to determine which underground structures could realistically create the observed signal patterns. Different sediment densities, buried ice distributions, and mineral compositions all alter radar behavior subtly. Processing the archive took years. That delay explains something unusual about the mission's timeline. Some of Zhurong's most important discoveries emerged only after the rover itself had already fallen silent beneath the Martian dust. The Nature Astronomy paper describing buried periglacial polygons appeared in November 2023, roughly 18 months after the last transmission. The shoreline analysis, examining the coastal escarpment and hydrated silica deposits, followed in 2024. The major revision to the Martian water timeline, arguing for sustained aqueous activity far later than expected, appeared in National Science Review in early 2026. Each study passed through peer review before publication. Peer review is the process where independent specialists examine the methods, calculations, and conclusions of a scientific paper before a journal accepts it. Researchers outside the mission team challenge assumptions, test interpretations, and search for weaknesses in the evidence. The process can take months or even years for major findings. That slowness matters. It means the conclusions surrounding Zhurong were not rushed reactions to exciting data. They survived sustained scrutiny from the broader planetary science community. Multiple independent reviewers examined the radar interpretations, mineral identifications, dating estimates, and geological models carefully enough for leading journals to publish them. And the work is not finished. The rover carried 6 scientific instruments operating simultaneously across different environmental systems. Together, they produced a data set large enough that mission scientists have suggested it may support new research publications for another decade. One operational year on Mars could realistically generate 15 years of peer reviewed science. That changes the way you think about mission lifespan. A rover's usefulness is not measured only by how far it drives or how long it survives mechanically. The true duration of a mission extends through every future analysis, every reinterpretation, and every new connection discovered inside the archived data years later. By that definition, Zhurong is still active, but understanding why its discoveries matter so much requires stepping outward from a single rover and looking at the broader picture. Mars exploration is now assembling across the planet simultaneously. For a brief period in 2021, Mars became crowded by its own standards. Three robotic explorers operated simultaneously across different regions of the planet, each examining a separate piece of Martian history, while sending continuous streams of data back toward Earth. That had never happened before. On February 18th, 2021, NASA's Perseverance rover landed inside Jezero crater. Orbital imagery had already revealed that Jezero once hosted a river delta, the fan-shaped deposit left behind when flowing water empties into a standing lake. Billions of years earlier, sediment washed through channels there and spread outward beneath shallow water. Meanwhile, far to the south, Curiosity continued climbing through Gale Crater after nearly a decade on Mars. Since landing in 2012, the rover had crossed ancient mudstones, sulfate-rich layers, and sedimentary rock formations, preserving an extended climate archive stretching across immense spans of time. Then came Zhurong and Utopia Planitia. 3 rovers, 3 geological environments, 3 independent scientific records developing simultaneously across the surface of another world. The differences between the sites mattered enormously. Jezero represented an ancient river and lake system. Gale preserved the remains of a long-lived crater lake, with layered sediments accumulating gradually over time. Utopia Planitia added something new, evidence tied not to lakes or rivers, but potentially to an ocean basin occupying a vast portion of the northern hemisphere. Individually, each mission described a local environment. Together, they began describing a planet. For the first time in history, scientists could compare real-time surface data collected from multiple distant Martian environments simultaneously rather than relying on isolated missions separated by decades. Patterns emerging at one site could now be checked against evidence from another. That comparison changed the scale of interpretation. Hydrated silica deposits appeared across all 3 locations, despite their geological differences. That consistency suggested silica-rich water chemistry may have been widespread across ancient Mars rather than restricted to isolated volcanic regions or singular hydrothermal systems. Layered sedimentary sequences at Gale and Utopia both revealed alternating wet and dry intervals, extending across long climatic transitions. The repeating environmental pulses identified beneath Utopia Planitia no longer looked local. They began resembling a planetary pattern. At Jezero, Perseverance identified sulfate minerals formed as water gradually evaporates and concentrates dissolved chemicals. Sulfates matter because they preserve the chemical fingerprints of drying environments extremely well. Their presence aligned closely with the retreating water history inferred from Zhurong's shoreline evidence and buried depositional cycles. The isolated discoveries began connecting into a coherent planetary narrative. Mars did not simply lose water everywhere at once. Different environments responded differently across time. Lakes shrank, groundwater retreated underground, surface conditions fluctuated. Some regions dried rapidly, while others preserved liquid environments far longer than expected. Three distant locations became reference points inside the same global system. And once that broader picture emerged, another possibility became difficult to ignore. If subsurface water persisted across multiple environments for immense stretches of time, then something may still remain hidden beneath the surface even now. At roughly 35 meters below the plane, the buried polygon structures traced a boundary through the subsurface, a transition zone where the physical properties of the ground changed sharply enough for radar signals to reflect back differently. That depth matters for a specific reason. On Earth, similar polygon systems often form near the upper edge of permafrost, the layer where frozen ground meets the more active material above it. In those environments, ice remains stable below while seasonal changes continue affecting the shallower sediment overhead. The fractures emerge precisely along that interface. Researchers studying Zhurong's radar data noticed the same possibility beneath Utopia Planitia. Years before the rover landed, NASA's Shared Orbital Radar Instrument had already suggested something remarkable hidden beneath the northern plains. A 2016 analysis estimated that Utopia Planitia might contain a subsurface water ice reservoir equivalent in volume to Lake Superior, approximately 12,000 cubic kilometers of frozen water buried beneath dust and rock. Lake Superior is enormous. It contains more surface freshwater than any other lake on Earth. If spread evenly across the continental United States, that amount of water would cover the entire country in a shallow inland sea. Zhurong could not directly confirm a reservoir on that scale. Its deep scanning radar resolved detail most effectively within the upper 100 meters of subsurface material, while the bulk of the proposed ice deposits may extend deeper underground beyond the rover's clearest detection range. But the geometry aligned intriguingly well. The buried polygons appeared exactly where scientists would expect the upper boundary of a major ice-bearing layer to begin, beneath dry, overlying sediment, yet shallow enough for ancient freeze-thaw activity to affect the transition zone above it. The radar profiles did not prove the existence of a massive reservoir outright. They strengthened the case considerably. If the shared estimates are even approximately correct, Utopia Planitia may contain one of the most accessible concentrations of frozen water anywhere on Mars outside the polar caps. That shifts the discussion beyond geology. Water is the central logistical requirement for sustained human activity on Mars. Every long-duration mission depends on it. Ice can be melted into drinking water, separated into hydrogen and oxygen through electrolysis, a process using electricity to split water molecules, and converted into rocket propellant for return launches. Water also absorbs radiation effectively, making it valuable for shielding habitats against cosmic radiation exposure. A human outpost without local water becomes vastly more difficult. The region Zhurong explored now appears unusually attractive, for exactly that reason. Over one operational year, the rover mapped subsurface structure, measured environmental conditions, analyzed surface chemistry, and constrained the probable depth of buried ice-related systems across the landing area. In effect, it conducted a preliminary site survey. Future astronauts may eventually arrive carrying drilling systems, habitation modules, and extraction equipment to a place first characterized by a small robotic rover crossing the plane alone. The scientific map Zhurong produced may one day become part of the engineering blueprint for humanity's first permanent foothold on another planet. But before human beings travel there, another machine almost certainly will, somewhere inside a secure laboratory on Earth. Scientists already know the exact measurement they want most from Mars. They want a sealed piece of Martian rock resting under controlled light, surrounded by instruments too large and delicate ever to survive a launch into space. That is the logic behind sample return. Rovers can photograph, drill, grind, heat, scan, and analyze material directly on another planet, but their instruments remain constrained by mass limits, power limits, and launch physics. Every gram launched toward Mars matters. Every scientific tool must survive radiation, vibration, and years of travel through space before functioning autonomously in brutal environmental conditions. The most sensitive laboratory equipment simply cannot make that trip. A high precision mass spectrometer, an instrument that identifies molecules by measuring atomic mass, may require hundreds of kilograms of supporting hardware and carefully controlled environmental systems. Some biological detection techniques need room sized shielding from vibration or contamination. Others require temperatures stable within fractions of a degree. Mars cannot currently host laboratories like that, but Mars samples can come here. China's next major planetary mission, Tianwen-3, aims to attempt exactly that. Current plans target a launch window around 2028 with the goal of collecting Martian material and returning it safely to Earth during the early 2030s. The landing location has not been officially confirmed, but Utopia Planitia remains under serious consideration for obvious reasons. Zhurong already surveyed the region extensively. Its radar mapped subsurface layers. Its instruments identified hydrated minerals, buried structures, and possible ice-related boundaries. The rover effectively created a geological guidebook for future drilling operations. That information changes mission planning dramatically. A sample return lander does not drill randomly. Depth matters, sediment age matters, mineral chemistry matters. The difference between drilling 2 meters deeper or selecting a slightly different deposit could determine whether ancient biosignatures remain preserved or destroyed. Zhurong narrowed the search. Meanwhile, NASA and the European Space Agency continue pursuing their own Mars sample return architecture centered around material already collected by Perseverance inside Jezero crater. But that effort has encountered major budget pressure and schedule uncertainty over recent years, slowing development timelines significantly. If Tianwen-3 launches on schedule and succeeds fully, China may become the first nation in history to transport verified Martian material back to Earth. And once those samples arrive, the scale of analysis changes completely. Scientists could examine isotope ratios, the relative abundance of atomic variants that preserve environmental history inside minerals. They could search for microscopic fossil structures using electron imaging systems capable of resolving features smaller than bacteria. They could analyze organic chemistry at concentrations measured in parts per trillion. Those measurements matter because biology leaves subtle traces, not dramatic fossils necessarily, sometimes only molecular asymmetries, carbon fractionation patterns, or mineral textures shaped indirectly by living systems. Tiny signatures, but detectable ones. If anything biological ever interacted with the sediments beneath Utopia Planitia, Earth-based laboratories finally possess realistic tools capable of finding the evidence. The question Zhurong sharpened may eventually be answered not on Mars itself, but inside a quiet laboratory on Earth, examining a small sample collected from ground, a silent rover, once crossed alone. In September 1976, another machine settled onto the same northern plain long before Zhurong existed, before modern planetary imaging, before high-resolution orbital mapping, before anyone seriously discussed buried Martian coastlines or subsurface climate cycles. That machine was Viking 2. The lander touched down inside Utopia Planitia, carrying one of the most ambitious scientific payloads ever sent to another world at the time. Its biology experiments were designed specifically to search for signs of life in Martian soil. Small samples were collected, heated, mixed with nutrients, and chemically analyzed for reactions associated with metabolism. For a moment, the results seemed extraordinary. Some experiments produced chemical responses that looked tantalizingly biological. Certain soil reactions released gases in ways researchers initially struggled to explain through ordinary chemistry alone. Debate erupted almost immediately across the scientific community. Then came the reinterpretation. Scientists eventually concluded that perchlorates, highly reactive chlorine based compounds, now known to exist widely across Mars, could produce misleading chemical behavior under Viking's testing conditions. The apparent signatures of metabolism faded back into ambiguity. But the deeper limitation was physical. Viking 2 could examine only the surface itself. The lander carried no ground penetrating radar. It could not image buried layers beneath the plane. It had no near infrared spectrometer capable of identifying hydrated minerals through reflected light signatures. Its cameras, astonishing by 1970s standards, lacked the resolution necessary to detect the subtle cracked textures later observed across the dune crusts near Zhurong's landing region. Viking saw only the exposed uppermost skin of Utopia Planitia. Below that thin surface sat 35 meters of buried polygon structures, layered sedimentary sequences recording repeated environmental cycles, possible ice boundaries, and geological archives extending backward nearly 4 billion years through Martian history. None of it was visible to the instruments available in 1976. The difference was not intelligence, it was instrumentation. If Viking 2 had somehow carried Zhurong's radar system, the trajectory of Mars science might have unfolded very differently across the following decades. Questions that emerged only recently may have appeared generations earlier. But that is not a criticism of Viking. The mission remains one of humanity's defining technological achievements. Reaching Mars successfully in 1976 required extraordinary engineering under computational conditions, primitive by modern standards. Viking laid the foundation that every later mission built upon. Its limitations reveal something broader about science itself. Discovery is constrained by what can be measured. Every instrument opens certain windows while leaving others sealed shut. A radar system reveals structures invisible to cameras. A spectrometer detects chemistry hidden from radar. Every generation believes it sees clearly until the next generation arrives, carrying tools that expose entirely new layers of reality underneath. That creates an uncomfortable question. If Zhurong transformed our understanding of Utopia Planitia using instruments unavailable 45 years earlier, what remains invisible right now beneath the Martian surface, waiting for technologies that do not yet exist? And among all the measurements Zhurong collected, one of the strangest came not from underground structures or mineral chemistry, but from something far quieter, moving invisibly through the crust itself. Long before cameras mapped valleys or radar traced buried layers, Mars left behind another kind of record entirely, one written invisibly into stone itself, through magnetism. Zhurong carried a fluxgate magnetometer for reading that record. A magnetometer measures the strength and direction of magnetic fields surrounding it. On Mars, those measurements matter because the planet no longer possesses a global magnetic field today. Roughly 4 billion years ago, the Martian core cooled enough that its internal dynamo, the churning movement of molten conductive material generating planetary magnetism, shut down permanently. The protective field vanished. Without that shield, solar radiation and charged particles from the sun gradually stripped away much of the atmosphere over immense stretches of time. The loss changed the planet fundamentally. But magnetism leaves fossils behind. When molten rock cools and solidifies inside an active magnetic field, iron-bearing minerals within the rock align themselves to that field automatically. After the rock hardens, the magnetic orientation remains locked into place. Scientists call this preserved signal remnant magnetism, essentially a frozen memory of the ancient field existing when the rock formed. Earth's own geological history was reconstructed partly through this process. Paleomagnetism, the study of ancient magnetic signatures preserved in rocks, helped scientists uncover continental drift and the movement of tectonic plates across Earth's surface over hundreds of millions of years. Invisible magnetic alignments became historical evidence. Mars preserves similar evidence. Orbital spacecraft had already detected strong magnetic remnants across the southern highlands, terrain among the oldest on the planet and formed while Mars still possessed an active global field. Utopia Planitia, by contrast, represents younger geological terrain created largely after the dynamo faded away. Zhurong confirmed that difference directly from the surface. The rover's measurements showed substantially weaker remnant magnetism across the landing region, consistent with the younger age scientists already associated with the northern plains. But within those weaker readings, something subtler emerged. Magnetic intensity varied from location to location, not randomly, spatially. As researchers compared the magnetic data against the radar profiles collected along the same traverse, correlations began appearing between magnetic variation and buried subsurface layering. Certain underground structures, mapped by radar, aligned closely with shifts in magnetic strength measured overhead. That mattered because the two instruments examined completely different physical properties. The radar mapped density contrasts and buried structural geometry. The magnetometer measured preserved magnetic orientation inside ancient rock and sediment. Neither system depended on the other to function. Yet both pointed toward the same broad chronology of environmental transitions within the subsurface. One timeline became two. Scientists could now cross-reference independent lines of evidence against one another, narrowing uncertainty and strengthening confidence in the dating of specific buried layers. It resembled two separate witnesses independently describing the same sequence of events with remarkable agreement. The Martian crust beneath Utopia Planitia was no longer merely layered, it was historically ordered. And while radar and magnetism slowly reconstructed the hidden history underground, another instrument aboard the rover spent its time watching something far more immediate, moving constantly above the surface: the atmosphere itself. Several times each Martian day, the rover paused quietly and listened to the air. Not metaphorically, literally. Mounted on Zhurong was a meteorological package continuously measuring surface pressure, temperature, and wind conditions across Utopia Planitia. While the radar examined buried history below ground, these instruments tracked something immediate and restless above it: the behavior of the Martian atmosphere in real time. Mars does possess weather. Its atmosphere is extremely thin, roughly 1% the density of Earth's at sea level, and composed mostly of carbon dioxide. During polar winters, temperatures become cold enough for carbon dioxide itself to freeze directly out of the air and accumulate as seasonal frost across the poles. Even so, the atmosphere remains active. At Zhurong's landing site, temperatures swung dramatically between day and night. During the coldest nighttime hours, readings approached minus 80 degrees Celsius. By afternoon, under direct sunlight, temperatures sometimes climbed above minus 20. That change exceeded 100 degrees within a single Martian day. At first, those numbers still sound far too cold for liquid water. Under ordinary conditions, they are. But Mars does not operate under ordinary chemistry. The surface contains widespread perchlorate salts, chemically reactive compounds capable of lowering water's freezing point substantially. That process matters enormously. When salts dissolve into water, they disrupt the formation of ice crystals and allow liquid water to remain stable at temperatures far below 0 Celsius. Scientists call this freezing point depression. On Earth, the same principle allows road salt to melt ice during winter storms. On Mars, it creates brief windows of possibility. The afternoon temperatures recorded by Zhurong, combined with perchlorate-rich sediment and occasional frost deposition, provided precisely the environmental conditions needed for transient liquid brines to form temporarily across dune surfaces. Not flowing streams, not standing pools, thin films of salty liquid appearing briefly before evaporating or refreezing. That mechanism helped explain the fractured crust patterns identified earlier near the landing region. The meteorological data also clarified how the dunes themselves evolved over time. Wind sensors recorded changes in direction, speed, and seasonal behavior throughout the rover's operational year. By comparing those measurements against surface morphology, scientists reconstructed how sediment migrated gradually across the plain and accumulated into the characteristic dune structures surrounding the site. The rover also documented multiple dust devils. Dust devils are rotating columns of warm, rising air that pull loose dust upward into spinning vortices. On Mars, they can tower kilometers high despite the thin atmosphere, crossing the plains silently while reshaping surface sediment in subtle ways over time. Some remove dust from solar panels, others deposit it. That distinction can determine whether a rover survives. The weather archive Zhurong collected now serves another purpose as well. Future robotic missions, and eventually human expeditions, will rely heavily on these atmospheric measurements when planning operations inside Utopia Planitia. Temperature management, dust mitigation, communication scheduling, and surface mobility all depend on understanding local environmental behavior precisely. Mars is not motionless. The air moves constantly above a surface, still exchanging material with buried layers below through slow chemical and thermal processes operating across immense spans of time. And beneath all those interacting systems sits one unresolved problem that Zhurong's discoveries made sharper than ever. There is an uncomfortable detail sitting underneath nearly every discussion about life on Mars, and without it, the entire search becomes difficult to understand clearly. The Martian surface is chemically hostile. In 2008, NASA's Phoenix lander confirmed the widespread presence of perchlorates across Martian soil. Perchlorates are highly oxidizing chlorine-based compounds capable of driving aggressive chemical reactions under the right conditions. On Earth, related compounds appear in rocket propellants and industrial oxidizers. Mars distributes them naturally across its surface. By themselves, perchlorates are already reactive, but combined with ultraviolet radiation constantly pouring through the thin Martian atmosphere, they create an environment especially destructive to organic chemistry. Organic molecules are carbon-based compounds associated with life and biological processes. Amino acids, cell membranes, proteins, nucleic acids all belong to that category. At the Martian surface, those compounds degrade rapidly. This realization transformed how scientists interpreted earlier missions. The ambiguous Viking biology experiments from the 1970s suddenly looked different once perchlorates entered the picture. Some reactions initially interpreted as possible metabolism could instead be explained through purely chemical oxidizing processes triggered by the soil itself. The soil had imitated biology chemically. That conclusion carries a second implication more troubling than the first. Even if ancient Martian organisms once existed and left behind organic traces near the surface, billions of years of perchlorate chemistry combined with ultraviolet exposure may have erased much of that evidence already. The surface becomes a poor archive. That is why shallow soil sampling alone is unlikely to resolve the life question decisively. The uppermost layers of Mars have spent immense stretches of time exposed directly to radiation and oxidizing chemistry, capable of dismantling fragile biological signatures, molecule by molecule. But the chemistry changes underground. Perchlorates form primarily through ultraviolet interactions occurring at or near the exposed surface. Deeper sediment layers remain shielded from direct radiation exposure. As depth increases, perchlorate concentrations are expected to decline while preservation conditions improve substantially. That changes where scientists look. The buried environments mapped beneath Utopia Planitia matter because they were once shaped by water, then sealed gradually beneath accumulating dry sediment. Those overlying layers may have acted like protective insulation, isolating older deposits from destructive surface chemistry for billions of years. A preserved biosignature on Mars, if one exists at all, is probably underground, not in loose surface dust exposed openly to radiation, but inside buried sediments deposited during wetter climatic intervals and protected afterward beneath stable geological layers. The deeper deposits identified by Zhurong suddenly become more than geological curiosities. They become candidate preservation environments. And now researchers know where those environments are located. The radar profiles constrain their depth, extent, and relative age while linking them directly to periods of ancient water activity. The rover did not uncover biology itself. It identified where future missions should search most carefully. In a sense, Zhurong produced a subsurface map marked with probabilities. The next mission follows those probabilities downward into the ground. But understanding why Mars preserved these environments at all requires stepping back further toward the shared origin of Mars and Earth and the small difference that separated their destinies completely. 4.6 billion years ago, there was no Earth and no Mars yet, only a rotating cloud of gas, dust, ice, and shattered mineral fragments orbiting a young sun still forming at the center of the solar system. Inside that cloud, the two worlds began together. Both planets assembled from the same raw material during the same brief geological era. Molten rock accumulated through collision after collision. Heavy elements sank inward toward forming metallic cores, while lighter materials floated upward into primitive crusts. Volcanoes erupted continuously across both young surfaces, releasing gases that thickened into atmospheres over time. Water arrived early. Some came locked inside minerals from the beginning. Some arrived later through comet impacts and water-rich asteroids crossing the inner solar system. Rivers formed, lakes collected, clouds moved overhead. For a while, the early histories of Earth and Mars looked surprisingly similar. Then the difference in mass began reshaping everything. Earth contains roughly 10 times the mass of Mars. That single advantage changed the thermal future of the planet completely. More mass meant stronger gravity and greater internal pressure. Greater pressure preserved internal heat longer. A hotter interior kept Earth's metallic core circulating dynamically for billions of years. That circulation generated a magnetic field. The field shielded Earth's atmosphere from direct erosion by the solar wind, the constant stream of charged particles flowing outward from the sunday. With the atmosphere protected, surface pressure remained stable enough for liquid water oceans to persist continuously. Climate cycles evolved, chemistry grew more complex. Eventually, life emerged and survived. Mars followed the same pathway only briefly. Its smaller size allowed internal heat to escape faster. The core cooled earlier. The magnetic dynamo shut down. Without global magnetic protection, the atmosphere gradually thinned under solar bombardment. Surface water froze underground, escaped into space, or retreated into isolated reservoirs beneath the crust. For decades, scientists treated that divergence as relatively abrupt. Mars became the failed version of Earth, a world whose habitability ended early and decisively. But the evidence gathered across Utopia Planitia complicates that story significantly. The transition now appears slower, more uneven, and far more prolonged than earlier models suggested. Mars kept holding on. Water cycled intermittently through the surface and subsurface long after the planet supposedly became hydrologically dead. Briny liquids formed under marginal conditions. Freeze-thaw systems persisted underground. Buried environments remained potentially habitable across immense stretches of geological time. Not comfortably habitable, persistently habitable. That distinction matters far beyond Mars itself, because planetary scientists use Mars as a comparative model for rocky worlds throughout the galaxy. If a planet only 1/10 Earth's mass can maintain liquid water-related environments for nearly 4 billion years, despite losing its magnetic field early, then the threshold for long-term habitability may be much broader than older models assumed. Worlds once dismissed as too small or too cold may remain biologically interesting far longer than expected. In that sense, Zhurong did more than revise the history of one planet. It added a new data point into humanity's estimate of how common life-friendly environments might actually be across the cosmos. And once you begin calculating those numbers seriously, the scale becomes difficult to absorb. Somewhere above the silent plains of Utopia Planitia, beyond the frozen atmosphere, Zhurong measured day after day. The night sky over Mars still contains the same immense population of stars that hangs above Earth. The scale is difficult to internalize. Our galaxy alone, the Milky Way, contains an estimated 200 billion stars spread across 100,000 light-years of space. For most of human history, we did not know whether planets around those stars were common or rare. Many scientists suspected planetary systems might be unusual accidents. Then the Kepler Space Telescope changed the calculation. By watching tiny drops in starlight caused by planets crossing in front of distant suns, Kepler revealed that planets are everywhere. The current estimate is staggering in its simplicity. On average, at least one planet exists for every star in the Milky Way. At minimum, 200 billion planets. Among those worlds, models suggest roughly 20 to 40 billion orbit within the habitable zone of their star, the orbital range where temperatures can allow liquid water to exist under suitable atmospheric conditions. Some are likely rocky. Some probably possess atmospheres. Some may have oceans, ice layers, volcanic systems, or underground aquifers hidden beneath frozen crusts. Before the recent findings from Mars, planetary habitability often appeared fragile and short lived. A rocky world might begin wet and active, then lose those conditions rapidly within a few 100 million years if its atmosphere collapsed or its internal heat faded too quickly. Mars itself seemed to support that interpretation, but the evidence assembled from Utopia Planitia complicates the timeline substantially. Water related environments persisted there far longer than older models predicted. Subsurface freeze thaw systems endured. Briny liquids appeared intermittently, even in relatively recent geological periods. The habitability window did not slam shut early. It narrowed slowly across billions of years. That changes the statistical landscape. If even 1% of habitable zone planets around Sun, like stars, maintain long term subsurface environments comparable to those suggested beneath Mars, the number of potentially life compatible worlds inside our galaxy alone rises into the hundreds of millions. And the Milky Way is only one galaxy. Current cosmological estimates place the number of galaxies in the observable universe at roughly 2 trillion. The numbers become so large that ordinary intuition fails completely. They stop feeling numerical and begin feeling philosophical, almost abstract, despite representing physical places scattered through real space. This is where the Fermi paradox sharpens. The paradox asks a simple question with uncomfortable implications. If habitable worlds are common and the universe is unimaginably old, where is everyone? Why have we found no confirmed evidence of extraterrestrial civilizations, no probes, no signals, no clear technological signatures crossing interstellar distances? One possibility is that life itself is extraordinarily rare, even when conditions appear favorable. The other possibility is distance. Civilizations may emerge briefly, separated by tens of thousands of light years and millions of years of time, each existing in isolation inside a galaxy too vast for easy contact. Zhurong did not solve that paradox, but it moved one important variable toward optimism rather than scarcity. And somewhere beneath the dust of Utopia Planitia, the next clue may already be waiting inside a buried layer of ancient Martian sediment. Scattered across the plains surrounding Zhurong's landing site were low formations that, at first glance, did not appear especially remarkable. They lacked the towering slopes we associate with volcanoes on Earth. No frozen lava fields surrounded them. No immense calderas opened across the horizon. They looked subdued. Yet, their shapes drew attention almost immediately. Circular cones, shallow pits, trough like depressions, narrow channels extending outward through the sediment. From orbit, they had been cataloged for years, but Zhurong provided the first close surface analysis of their structure and distribution. The interpretation that emerged was cautious but significant. These may have been mud volcanoes. Mud volcanism works very differently from ordinary volcanism. Instead of molten rock erupting from deep magma chambers, mud volcanoes form when pressurized subsurface fluids, usually water mixed with clay and fine sediment, force their way upward through fractures in overlying rock layers. The material breaches the surface slowly, piling into low mounds or collapsing into pitted depressions after pressure releases. On Earth, these systems appear in surprisingly diverse places. Azerbaijan contains hundreds of active mud volcanoes scattered across its dry terrain. Similar systems exist beneath the Gulf of Mexico and throughout the South Caspian Basin. Some release methane continuously. Others carry mineral-rich slurries upward from kilometers below the surface. And many host life, not surface plants or animals, but microbial ecosystems living entirely underground. These organisms survive through chemosynthesis, a biological process that extracts energy from chemical reactions instead of sunlight. They inhabit dark fluid pathways where water, rock, salts, and dissolved gases interact continuously over immense periods of time. Zhurong's observations did not confirm biology. They did something narrower and scientifically precise. They identified geomorphology, meaning landform structure, consistent with subsurface fluid movement in a region already known to contain buried water-related deposits. That convergence matters. The radar had already mapped layered sediments and polygon structures associated with freeze-thaw environments. Mineral analysis had already revealed hydrated compounds requiring sustained interaction with liquid water. The possible mud volcanic features added another independent line of evidence, suggesting that Utopia Planitia was not simply storing ancient water passively underground. It may have been circulating it. If fluids once moved upward through these structures, they would have created exchange pathways between deep subsurface reservoirs and the surface environment above. Water, salts, gases, and heat could all migrate through those fractures slowly across geological timescales. On Earth, exactly those interfaces often become biological refuges. But the Martian interpretation remains provisional. No rover has drilled directly into one of these candidate structures. No sample has been extracted from their interior. Planetary scientists remain careful with the language because morphology alone cannot fully establish origin. Wind erosion can occasionally imitate volcanic forms. Ancient ice collapse can create similar depressions. Still, when multiple datasets converge independently on the same environmental history, confidence grows. And beneath the layered sediments of Utopia Planitia, another possibility remains hidden, one far larger than dunes, polygons, or mud cones alone. By this point in the story, the evidence begins converging toward a single underlying conclusion. The layered sediments, the buried polygons, the hydrated minerals, the transient liquid films on dunes, the candidate mud volcanic structures, even the geometry of the ancient shoreline all point in the same direction. Water shaped this place, not briefly, not superficially, persistently, across immense spans of Martian history. The strongest orbital estimate came years before Zhurong arrived. NASA's shared radar instrument, operating aboard the Mars Reconnaissance Orbiter, analyzed reflections from beneath the plains of Utopia Planitia and concluded that the region could contain a subsurface ice deposit comparable in volume to Lake Superior. That number deserves perspective. Lake Superior contains roughly 12,000 cubic kilometers of water. Spread evenly across the continental United States, that quantity would cover the entire country beneath approximately 1.5 meters of water. It is the largest freshwater lake on Earth by surface area, vast enough to generate its own localized weather systems. And something comparable may exist beneath the Martian ground. Zhurong's radar could not directly image the full depth of that reservoir. Its deepest scanning mode resolved structures most effectively within the upper 100 meters of crust, but the rover identified polygon boundaries and layered transitions exactly where the upper margin of buried ice would theoretically begin. The surface evidence aligned with the orbital evidence. That matters operationally as much as scientifically. Mars possesses enormous water reserves at its polar caps, but the poles create severe engineering problems for human missions. Temperatures plunge dramatically lower there. Seasonal darkness lasts for months. Communication geometry becomes more difficult. Surface conditions fluctuate intensely through the Martian year. Utopia Planitia sits instead within the northern mid-latitudes. The terrain is comparatively flat, Seasonal conditions remain less extreme, landing risks are lower, surface mobility is easier. Now, because of Zhurong, the subsurface structure, mineral composition, weather behavior, and sediment history of the region are also documented in unprecedented detail. The practical implications are profound. Water on Mars is not merely something astronauts would drink, it becomes infrastructure. Ice can be melted into liquid water for human consumption and agriculture. Through electrolysis, meaning the splitting of water molecules using electricity, it can also produce hydrogen and oxygen. Oxygen supports breathing. Combined hydrogen and oxygen create rocket propellant. A settlement with reliable water becomes dramatically more sustainable. Seen across the long horizon of history, the quiet 1 year Zhurong spent driving across those plains may eventually be interpreted differently than we interpret it now. Not simply as a scientific expedition, but as an early site survey for humanity's first permanent foothold on another planet. Perhaps one day people will stand inside pressurized habitats beneath the pale sky of Utopia Planitia, recycling air, extracting water from buried ice, and walking across ground first mapped in detail by a silent rover now resting beneath layers of Martian dust nearby. But before imagining that future too clearly, it is worth pausing with what this mission already changed in the present. Measured against ordinary human scales, the achievement seems almost absurdly small. Zhurong traveled 1.2 miles across the surface of Mars. Its operational life lasted roughly 1 Earth year. The rover itself weighed about 240 kilograms, close to the mass of a large motorcycle resting quietly in a garage. And yet, we launched it across nearly 100 million miles of interplanetary space to accomplish that journey. The ratio feels disproportionate at first. But distance alone has never measured the value of exploration. Context does. A single kilometer walked through unknown terrain can matter more than crossing an entire familiar continent. What matters is whether the ground beneath the wheels changes what we understand about reality. In Zhurong's case, it did. Within that short traverse, the rover identified evidence consistent with an ancient shoreline bordering a vanished ocean basin. It detected hydrated minerals requiring sustained liquid water. It mapped buried polygon structures formed through repeated freeze-thaw cycles. It revealed layered geological histories spanning billions of years. It documented modern conditions capable of producing transient saline liquids. It detected magnetic variations aligned with subsurface chronology. All of it emerged from a route short enough that many people could walk it casually in under half an hour on Earth. The concentration of scientific return is extraordinary. But this was not luck alone. Several conditions aligned simultaneously. The landing site intersected multiple geological histories in one region. The rover carried instruments sensitive enough to resolve structures that previous missions could not see. And perhaps most importantly, planetary science itself had matured. Researchers finally knew which questions to ask and which signatures mattered. That combination changes everything. There is a recurring pattern throughout the history of exploration, one visible from ocean voyages to deep-sea probes to planetary missions. Transformative discoveries rarely come from scale alone. They happen when the correct instrument reaches the correct location at the precise moment human understanding becomes ready to interpret what it finds. Zhurong embodies that pattern almost perfectly. Its science team expected refinement. They expected confirmation. Instead, they encountered contradiction, complexity, and evidence that Mars remained hydrologically active far longer than prevailing models allowed. That distinction matters deeply. There is a difference between performing exploration as spectacle and performing exploration as inquiry. Spectacle seeks validation of what we already hope to see. Inquiry accepts the possibility that reality may answer differently. Zhurong answered differently, and it did so in almost total silence. No wind carried across microphones for human ears. No voices echoed through the plains of Utopia Planitia. The rover moved alone through a landscape where no living thing has ever been confirmed to exist, transmitting streams of compressed data across space toward a distant species trying to reconstruct another world's history from faint electronic signals. Now it sits motionless beneath accumulating dust. But even inactive, it continues producing meaning. Papers continue appearing, models continue evolving, assumptions continue shifting. A silent machine on an empty plane continues changing the way an entire planet is understood. That silence itself becomes part of the story. The plains of Utopia Planitia are not silent in the ordinary sense of the word. Wind still crosses the basin floor. Dust moves in long shifting curtains across the horizon. Small vortices rise and collapse. Temperature swings ripple through the ground every Martian day, expanding and contracting the crust by microscopic amounts. The planet is active, but isolation there exists on a scale the human mind struggles to emotionally process. At every moment of Zhurong's operational life, the nearest human beings were aboard the International Space Station, orbiting Earth roughly 400 kilometers above its surface. Yet Earth itself remained tens of millions of kilometers away from Mars. Depending on orbital position, the separation ranged from approximately 55 million to more than 400 million kilometers. No human being was ever remotely close to that rover. No voice crossed the plane. No footsteps approached its tracks. No emergency rescue was possible. Nothing alive stood within 100 million miles of the machine at any point during its existence. And still it worked. Because Mars is too distant for direct control, every command required patience. Radio signals traveling at light speed still needed between 3 and 22 minutes to cross the distance each way. Real-time piloting was impossible. Zhurong could not be driven like a remote-controlled vehicle. Its routes were planned carefully in advance, uploaded through deep space antennas, then carried out autonomously. The rover made countless operational decisions entirely alone. It performed hazard avoidance calculations. It evaluated wheel placement. It monitored internal temperatures and battery conditions. It positioned instruments. It paused when terrain became uncertain. It navigated a world no organism from Earth had ever physically entered before. Then it spoke through radio waves. The information it gathered left Mars at the speed of light, crossed interplanetary space, arrived at receiving stations in China, passed through servers and processing systems, and eventually reached teams of scientists who spent months disentangling what those streams of numbers actually represented. A layered crust, a buried polygon, a hydrated mineral signature, a magnetic variation, meaning emerged slowly. And the meaning that emerged altered the history of an entire planet. The world Zhurong explored had remained environmentally active far longer than earlier generations of science believed possible. Water persisted. Climate cycles endured. Subsurface systems evolved gradually instead of collapsing abruptly into permanent sterility. There is something almost painfully elegant about that chain of events. A machine now likely inactive forever, resting beneath accumulating dust on an ancient basin floor, continues telling us that Mars itself resisted death longer than we understood. The rover fell silent while revealing that the planet beneath it had once remained dynamic, marginally habitable, and chemically alive across immense spans of time. The contradiction lingers quietly in the mind, a silent machine explaining a once living world. And tonight, while Earth turns beneath crowded skies filled with cities, oceans, voices, and weather, Zhurong still remains where it stopped, wheels settled into the soil of Utopia Planitia, facing a horizon no human eye has ever directly seen. For decades, the standard narrative of Mars followed a clean and orderly progression. The planet began warm and wet during the Noachian era more than 4 billion years ago. Rivers carved valleys, lakes collected in craters, perhaps an ocean spread across the northern lowlands. Then the decline began. The Hesperian period marked the collapse. Volcanism faded, the atmosphere thinned, surface water disappeared. By the Amazonian era, beginning roughly 3 billion years ago, Mars was understood as essentially finished, a cold desert entering permanent geological exhaustion. The timeline appeared simple, but Zhurong complicated that simplicity profoundly. Its measurements revealed evidence that water-related activity did not vanish in one decisive planetary collapse. Instead, the record shows interruptions, returns, cycles, and persistence. Freeze-thaw systems continued underground. Briny liquids formed at the surface under favorable seasonal conditions. Sedimentary layers recorded alternating wet and dry intervals spanning immense stretches of time. Mars did not stop all at once. It adapted downward. As surface conditions deteriorated, habitable environments retreated into protected regions beneath the ground, where temperature fluctuations softened, radiation weakened, and water could persist in frozen or transient liquid states. The planet shifted gradually from openly habitable conditions toward marginal subsurface survivability. That distinction changes more than a timeline. For many years, planetary habitability was framed almost as a binary category. A world either possessed the right ingredients for life or it did not. Earth remained active and biologically rich. Mars crossed a threshold and became dead. Zhurong suggests reality may operate more gradually than that. Habitability may fade the way twilight fades, slowly and unevenly, lingering in protected pockets long after the broader environment becomes hostile. A planet can lose oceans and still maintain buried reservoirs. It can lose atmosphere and still preserve liquid films under specific chemical conditions. It can become barren at the surface while remaining chemically dynamic below. Mars now appears less like a failed Earth and more like a world fighting against decline for billions of years. That reframing carries enormous implications beyond our solar system. Astronomers already know that rocky planets are common throughout the galaxy. Many orbit inside habitable zones briefly during their star's evolution. But if subsurface environments can extend planetary habitability dramatically beyond surface collapse, then many worlds previously dismissed as sterile may still possess chemically active interiors. Invisible oceans may exist beneath frozen crusts. Buried aquifers may persist beneath radiation-blasted deserts. Chemosynthetic ecosystems, meaning organisms powered by chemical reactions instead of sunlight, may survive entirely underground where telescopes cannot detect them. From interstellar distances, such planets would appear dead. Their atmospheres might reveal nothing unusual. Their surfaces might look frozen and inactive. Yet beneath the crust, life could continue quietly for geological ages, and we would have almost no way to know from Earth. That possibility changes the emotional texture of the search for life itself. The universe stops feeling divided cleanly between living worlds and dead ones. Instead, it begins to resemble a spectrum of hidden persistence where biology may survive in darkness, underground, waiting beyond the reach of ordinary observation. Far beneath Earth's forests, oceans, and cities, another biosphere exists almost entirely out of sight. It lives inside fractures in rock, inside groundwater trapped under continents, inside porous mineral layers buried kilometers below the surface. We discovered it surprisingly late. In 2019, the Deep Carbon Observatory concluded a decade-long international investigation involving more than 1,200 scientists across 52 countries. Their findings reshaped biology itself. Earth's deep subsurface contains an estimated 15 to 23 billion tons of microorganisms living entirely without sunlight. The scale is difficult to picture. This underground biosphere may contain biomass comparable to all surface life combined. Vast microbial ecosystems survive in darkness, isolated from the atmosphere for millions of years, sustained not by photosynthesis but by chemistry. Water interacts with rock, minerals exchange electrons, tiny organisms harvest that energy and continue living slowly, patiently, deep underground. Before drilling technology improved, science had no idea this world existed. The implications for Mars are immediate. If a comparable subsurface biosphere ever developed there, it would remain completely invisible from orbit. Telescopes would never detect it. Surface cameras would never see it. Even a rover crossing directly above it would notice nothing unless its instruments could probe downward into the buried layers. That limitation matters enormously. The deepest direct drilling ever achieved on Mars penetrated less than 1 meter beneath the surface. Zhurong's radar extended observational reach to approximately 100 meters, but the most stable liquid water environments on present-day Mars may exist far deeper still, potentially several kilometers below the ground, where pressure and geothermal heat allow brines to remain liquid. Between 1 meter and several kilometers lies an enormous unknown, not a small missing detail, a frontier. Zhurong did not close that gap, but it transformed the gap from abstraction into geography. The rover mapped buried layers, identified water-modified sediments, constrained the depth of polygon structures, and revealed where ancient freeze-thaw systems once operated. For the first time, scientists gained a structured subsurface framework showing which regions are most promising for future drilling. The mission effectively drew a vertical map of hidden possibility. Somewhere beneath Utopia Planitia, there may be layers sealed away from ultraviolet radiation for billions of years. Sediments once saturated with water may still preserve chemical traces from ancient environments. Mineral boundaries may contain concentrations of salts, organics, or isotopic patterns inaccessible at the surface. If Mars ever hosted microbial life, the surviving evidence is probably there, underground, protected by depth and time. Reaching it will require machines far more ambitious than any rover yet built. Deep drilling systems, sterile sample handling, autonomous underground exploration, missions operating not only across the Martian landscape, but downward into it. And until those missions arrive, the question remains suspended beneath the surface, hidden under layers Zhurong could map but not penetrate fully. Meanwhile, the rover itself still rests above that buried archive, motionless in the dust of Utopia Planitia, its batteries silent, its wheels half settled into the sediment, having carried us just far enough to understand how much deeper the real search may need to go. Long before rockets existed, people looked upward and explained the sky through fire. In ancient Chinese mythology, Zhurong was the god of flame, warmth, and the southern heavens. Fire was not merely destruction in these traditions, it was transformation. Heat made harvests possible. Heat shaped metal. Heat separated living worlds from frozen silence. Thousands of years later, that name crossed interplanetary space. The rover, called Zhurong, arrived on a planet whose internal fire had faded almost beyond recovery. Mars once possessed molten energy sufficient to power a magnetic dynamo, drive volcanism, recycle minerals, and maintain stable surface water. Over immense stretches of geological time, that heat diminished. The core cooled. The magnetic field weakened and vanished. Atmospheric protection collapsed. Oceans disappeared into space, stone, and ice. The planet entered a long decline. But decline is not the same thing as instant death. That distinction became the center of Zhurong's mission. The rover spent 1 year crossing the floor of Utopia Planitia, examining the residue left behind by a world struggling to remain active. Every instrument contributed another fragment to the chronology. Radar traced buried cycles of water activity. Surface chemistry revealed hydrated minerals. Weather data showed conditions still capable of producing transient brines under the right circumstances. The deeper the evidence accumulated, the stranger the timeline became. Mars was not simply warm once and cold afterward. It resisted. Water returned intermittently. Ice interacted with sediment. Freeze-thaw cycles continued deep underground long after surface habitability supposedly ended. Geological processes lingered billions of years beyond the neat boundaries older models had imposed. Zhurong measured those lingering processes directly. There is something remarkable in that symmetry. A rover named for fire arriving at a world where the fire nearly vanished, then discovering that traces of warmth and movement persisted far longer than anyone realized. Not metaphorically, physically. The numbers themselves carry enough weight. A planet 4.6 billion years old. A rover weighing 240 kilograms. A traverse of 1.2 miles across a basin 3,300 kilometers wide. Scientific papers still emerging years after the machine stopped communicating. No embellishment improves that reality. And the rover itself became part of the story it was studying. Its operational life ended because sunlight no longer reached its dust, covered solar panels with sufficient intensity to restore power. A machine dependent on energy slowly fell silent on a world defined by lost energy. Yet the silence was incomplete. The stored data continued traveling through laboratories, journals, conferences, and analysis software. Long after the rover ceased transmitting, it kept contributing to human understanding. Its observations remained active even while the machine itself rested motionless beneath the Martian dust. From a certain angle, that continuation feels almost inseparable from the mission's deeper meaning. A civilization on one world built a machine named for fire and sent it to another world to learn how warmth disappears, how habitability fades, and how traces of activity can persist quietly long after the visible surface appears finished. And from that same angle, the story still does not feel concluded. Above the horizon of Utopia Planitia, one object in the night sky shines with unusual steadiness. It does not flicker like distant stars through the thin Martian atmosphere. It moves slowly across the darkness with the measured rhythm of a neighboring world. That object is Earth. From the position where Zhurong now rests, silent beneath accumulated dust, Earth appears as a bright blue-white point suspended over the basin floor. Depending on the orbital geometry between the planets, the distance varies enormously, sometimes approaching 400 million kilometers, sometimes shrinking near 55 million. Averaged across the cycles, Roughly 100 million kilometers separate the rover from everything human, and yet the planet remains visible. Under ideal conditions, Earth can cast an extremely faint shadow across the Martian surface, not enough for human eyes to notice easily, but enough to register instrumentally. A tiny source of light crossing an immense darkness. Carl Sagan described Earth as a pale blue dot in 1990 after Voyager. One photographed it from 6 billion kilometers away near the edge of the solar system. The emotional effect from Mars is strangely similar. Distance compresses complexity. Entire civilizations collapse into brightness no larger than a point. Inside that point exists everything familiar. Every language, every ocean, every extinct species, every memory anyone has ever carried, every observatory, laboratory, launch pad, and radio antenna involved in sending Zhurong across interplanetary space exists inside that small light above the Martian horizon. So do the people who waited for its transmissions. The rover itself moved in the opposite direction, away from Earth, away from the only known biosphere in the universe. A machine roughly the size of a motorcycle crossing a dead ocean basin with 6 scientific instruments, searching for evidence that another world once possessed conditions suitable for life. The scale of the engineering is extraordinary, but the scale of the question is older still. Are living systems rare accidents, emerging only once through improbable chemistry? Or does biology arise naturally whenever rock, water, energy, and time remain together long enough? Zhurong did not answer that question directly. No rover has. But the mission altered the statistical landscape around it. It extended Mars's habitable timeline by billions of years. It identified buried environments protected from destructive surface chemistry. It mapped layers where water persisted far later than expected. The possibility, space widened, not certainty, possibility, and sometimes that matters just as much. Because every revision forced scientists toward the same realization. If the evidence we seek is buried beneath meters or kilometers of sediment, then nearly all previous Mars exploration has sampled only the outermost skin of the planet. We have barely started looking downward. The strange thing is how recent this realization truly is. For decades, humanity searched Mars, mostly across its surface, while some of the most compelling environments may have been hidden underground the entire time. Now we know enough to recognize the depth of what remains unexplored, and for the first time, missions are beginning to be designed around that understanding. Night settles slowly across Utopia Planitia. The temperature falls toward minus 80 degrees Celsius. The thin carbon dioxide atmosphere, barely 1% the pressure of Earth's at sea level, carries little heat and almost no sound. Dust shifts occasionally across the basin floor, driven by distant winds, moving through darkness too cold for liquid water at the surface. The rover remains still. Its solar panels are layered with fine Martian dust accumulated through storms and seasons. Its wheels rest half-pressed into the regolith where they stopped in May 2022. The instruments are powered down. No radio transmission leaves the antenna. No movement interrupts the plane surrounding it. Only the sky changes. Without a thick atmosphere to scatter artificial light or moisture, the Martian night appears dense with stars. The sky resembles what humans on Earth see only from isolated mountain summits or deep ocean deserts far from cities. Constellations sharpen, dim stars emerge. The Milky Way stretches overhead with unusual clarity. Among those stars is Earth, a small blue-white point crossing slowly above the horizon as Mars rotates beneath it. Somewhere on that distant point, scientists continue examining data Zhurong transmitted years earlier. Terabytes of radar reflections, mineral spectra, magnetic readings, atmospheric measurements, and imaging files remain stored in archives and server arrays, waiting for new analysis techniques, new comparisons, and new questions. The rover became silent. The investigation did not. Even now, connections between data sets may still be undiscovered. Layer relationships hidden in the radar profiles may reveal additional climate cycles. Mineral signatures may align with future orbital observations. Subsurface models may sharpen as computing methods improve. The mission continues in another form. During the coming decade, new spacecraft are expected to reach Mars carrying drills capable of penetrating deeper than previous missions attempted. Sample return architectures are being refined. Laboratories on Earth are preparing analytical systems sensitive enough to detect isotopic anomalies, microscopic fossil structures, and organic compounds at concentrations impossible to measure remotely. Those future investigations will not begin from ignorance. They will begin from the map Zhurong helped build. And if one of those missions eventually recovers evidence that life once existed beneath the Martian surface, the discovery will arrive attached to a chain of earlier observations leading backward through years of accumulated science to a quiet rover in Utopia Planitia, a machine that traveled 100 million miles to drive 1.2. Its operational life lasted roughly a year. Its scientific consequences may last generations. There is something fitting about the pace of it all. Mars did not reveal its history quickly. The planet preserved its records across billions of years, beneath layers of dust, ice, sediment, and stone. Understanding was never going to arrive suddenly. So the rover waits in darkness while the work continues elsewhere. The night over Utopia Planitia is long, the cold is immense, but the question that carried Zhurong across interplanetary space remains active, patient, and unfinished. Somewhere between that pale blue point in the sky and the silent rover beneath it, the answer already exists. We simply have not reached it yet.